Good morning, good afternoon, and good evening, everyone. My name is Chris Barrett. I'm a professor at Cornell University, and it's my great pleasure to welcome you today to our webinar on using big data and machine learning to predict poverty and malnutrition for targeting, mapping, monitoring, and early warning. This is a joint activity by the Food Security Portal facilitated by the International Food Policy Research Institute, IFPRI, and supported by the European Commission, and of the research project Harnessing Big Data and Machine Learning to Feed the Future, run out of Cornell University and funded by the United States Agency for International Development, USAID, with financial support also from the CGIAR research program on policies, institutions, and markets. In this project, we combine the latest advances in satellite vegetation remote sensing and physical measurement with other publicly available data processed using accessible machine learning techniques to explore the potential to provide accurate, timely, and lower cost monitoring of key Feed the Future outcome indicators, such as asset poverty and nutritional status at the subnational community level in low-income Feed the Future countries. The resulting indicators enable higher frequency monitoring and adaptive targeting, as well as careful impact evaluation of Feed the Future and other interventions when combined with rigorous research designed around project or program participation. Last week, we hosted a webinar that discussed some of the new Earth observation data products generated by the project, in particular by the labs of Professors Li-Shu Hu of the University of Alabama at Huntsville and Professor Ying Sun of Cornell University. A recording of that webinar is available on the Food Security Portal hosted by IFPRI and on the project website at Cornell, which Midabulumala will present at the end of today's webinar. Today, we have three outstanding speakers. Dr. Linda McBride, who was formerly with St. Mary's College and now is with the U.S. Census Bureau Center for Economic Studies, Dr. Yanyan Liu from IFPRI, and Chris Brown of Cornell University, as well as a distinguished discussant, Dr. Rob Voss, Director of the Markets, Trade, and Institutions Division at IFPRI. They will discuss advances in the use of Earth observation data and machine learning data science methods to improve monitoring, mapping, and nowcasting of various indicators used by the U.S. government's Feed the Future program and other development and humanitarian agencies. At the end of today's session, Midabulumala of Cornell will walk us through the research project website and the annotated Python, R, and Stata code that users can find there and that they can adapt for their own use of these methods. So if you have questions today, please feel free to submit them in the side panel at any time where it says questions box. I will read them during the Q&A session that will follow the discussant's remarks. And please note that this webinar will be recorded. The slides and recording of the session will be posted on the Food Security Portal's website and on the Cornell Project website. I will introduce each speaker as they come in. To begin, I'm pleased to introduce our first presenter, Dr. Linda McBride, who will provide an overview of the topic and a review of current frontiers in the application of big data and machine learning methods to development and humanitarian programming. Over to you, Linda.
Thanks so much, Chris, and good morning, everyone. Thanks for joining us so early. This paper is titled Predicting Poverty and Malnutrition for Targeting, Mapping, Monitoring, and Early Warning, and I'm thrilled to announce that it was just published in Applied Economics Perspectives in Policy. Next slide, please. All right, in this paper, we begin with the question, can big data and machine learning revolutionize poverty and malnutrition, mapping, targeting, monitoring, and evaluation and forecasting? And the answer is yes. However, we want to encourage agencies that rely on these methods, as well as model and tool and map developers, to think carefully about the trade-offs inherent in the inputs and outputs to these methods. In particular, we emphasize in this paper that agencies' needs vary. The temptation with machine learning and big data is to take all the data, pour it into the right-hand side of the model, and get the best prediction possible. But that's not necessarily what agencies need. It's not necessarily the most cost efficient. It's not necessarily the most effective at capturing different types of deprivation. So we emphasize that both agencies and developers should consider the purpose and the use case of the tool that they're developing. And we encourage this thoughtful consideration by emphasizing a set of questions or trade-offs that both should go through. So in particular, we asked what type of deprivation is being investigated. What is the time horizon for the model? Are we trying to predict contemporaneously? Are we trying to nowcast? Are we trying to forecast? How transparent and accessible to the general public does the final model need to be? There can be political economy considerations behind a given map, tool, or method. How onerous and consequently how costly is the data collection and curation task? In some cases, we want a map that can be a map or a tool that can be readily updated. In that case, we need to carefully consider the cost of the inputs. And these questions amount to what Zula et al. Articulate as the agency's objective function. So throughout this paper, we try to stay focused on that. Next slide, please. So we encourage practitioners and model developers to fit their tools to the explicit tasks. And then we express that through a series of considerations. Is the tool intended to target households, or is it intended to develop a map? Whereas targeting identifies poor, malnutrition, malnourished people or households, a map is intended to provide a geographic depiction of deprivation. We also note that there's tension between the asset-based theory and empirics of poverty traps. We know that structural poverty follows asset dynamics. However, the temptation in machine learning and big data is to just obtain the most predictive feature set, which doesn't necessarily always rely on these key asset variables. So we highlight this tension between structural and stochastic forms of deprivation. In addition, we encourage agencies and model developers to carefully consider whether they're interested in a static or a dynamic model, whereas most of these models are static, predicting poverty or deprivation in the next period or even contemporaneously. If we're interested in early warning, then we might be more interested in changes over time, which is a different task altogether and requires different inputs. Finally, we highlight some of the data needs for improved mapping, monitoring, targeting, and early warning. Next slide, please. All right, the innovations in poverty targeting have tended towards leaner and leaner models, and this is very cost efficient for agencies that use these targeting models. So the scorecard approach, which was pioneered by Mark Schreiner and further developed by Krishagar and others, uses proxy means test, uses machine learning for dimension reduction and to get a highly predictive feature set, and then validates this using out-of-sample testing. Additional innovations in this field are Nippenberg et al. Using high-frequency data, and Altendog, who very cleverly use administrative data to develop their proxy means test targeting tool, which saves agencies a great deal of money in terms of initial data collection. Next slide, please. All right, on the mapping front, the trend is in the other direction. Whereas with targeting, we're interested in leaner and leaner models and innovations that draw on lean data. With mapping, the trend is to draw on more and more diverse data sources. So some of the exciting developments in this region are Bloomstock et al. His lab is using call data records to really innovate actually both poverty targeting and mapping. The use of night lights, daytime satellite imagery, NDVI, and other remotely sensed data. And those who attended the webinar last week will have gotten an introduction to SIF and LST. The combination of data sources, like I mentioned, for more productive or more accurate mapping models, and also looking at a combination of outputs. This might include the multidimensional poverty index, as produced, a map that was produced by Procure and Jack and Nguna and McSherry. And in the paper that Chris Bound will cover, the multivariate prediction of correlated outcomes. If we have an inkling that poverty and malnutrition are correlated, can we harness those correlations for better predictions? And then finally, Hirsch et al. Have really emphasized that open source data is important for agencies' mapping efforts. Next slide, please. All right, some of the frontiers here that haven't quite been tackled is better targeting or in mapping the multidimensional nature of deprivation. And again, we'll hear Chris Brown's paper shortly, which makes a step in this direction. Better predicting low probability and noisy outcomes such as stunting and wasting. Because these are low probability and tend to be measured with noise, they're much more difficult to predict, but also getting accurate predictions is extremely important. We are confronted by limited data availability, especially for the populations that are most vulnerable. Data like call data records or nightlights tend to give us better information about relatively wealthier households. Whereas if we're interested in the poorest of the poor, these exciting new data sets might not give us as much information on those populations as we would like. And then finally, a next step in this area is not just targeting and mapping deprivation, but also identifying the determinants of the deprivation. And Ye et al. Take a important step in this direction. Next slide, please. All right, the next series of trade-offs we emphasize is identifying structural versus stochastic deprivation. Now, the exciting thing is that recent mapping models are doing really well in predicting asset poverty across space and over time. And I think that will continue to develop. Each new paper that comes out offers, higher predictive accuracy, which is very exciting. Some of the frontiers in this field are better parsing the persistently poor, the structural poor, from the dynamically mobile. Another way of saying this is better mapping the well-being dynamics behind the deprivation that we observe. An exciting innovation and frontier in this field is the notion of resilience targeting and resilience mapping, as pioneered by Barrett and Constas and Cisse and Barrett. Next slide, please. The next series of trade-offs we consider are static versus dynamic targeting, mapping, early warning, and etc. The idea here is that most of the models that are available, most of the models we develop tend to be static. We're predicting levels in some geographic area or in some future time period. Whereas if we're interested in early warning, we might be more interested in changes over time. So some of the exciting innovations in this field have been pioneered by Mude et al. And Lentz et al. Using high frequency data. They're able to develop food security early warning systems. Tang et al. And Ye et al. Also demonstrate that the use of convolutional neural networks trained on changes over time rather than levels can predict changes in future consumption or asset wealth. And then Brown et al. In the paper he'll discuss produces both contemporaneous and sequential prediction of correlated asset wealth and malnutrition indicators. Next slide, please. Some of the frontiers in this field, or rather, this first bullet point is how we might tackle some of these frontiers, is accessing more high frequency data. Again, if we shift our focus from the prediction of levels to the prediction of changes, I think we can make progress in this field. And then finally, integrating time series statistics with machine learning methods could be a really promising way forward. Next slide, please. Finally, it's probably not news to this audience that there is a serious undersupply of the global public good of the collection, standardization, updating, and open access of curation of key variables, such as, for example, household level assets. And that poses a challenge to the use of big data and machine learning for these development of these tools. Our models are only as good as the data that feed into them. Another constraint we're confronted with is that we can only reliably predict states and processes that have been previously observed in the data, which is to say, as climate change changes the data generating process, our models are going to do a poorer and poorer job of anticipating what's to come. The good news is, silver linings, I suppose, is that COVID has likely accelerated trends towards more creative data collection. Blumenstock has a nice Nature article on this, just highlighting the creativity we've had to embrace to collect household level, individual level data in the face of limited social interaction. Next slide, please. All right, so in summary, it's very exciting. Big data, machine learning methods are revolutionizing what we can do in terms of mapping, targeting, monitoring and early warning, monitoring, evaluation, and early warning. However, we really encourage thoughtful consideration of the purpose and use cases of whatever is being developed. Data availability and creation may remain serious limitations. This was just a quick overview. For more details, check out the full article that's available at Applied Economics Perspectives and Policy. Thanks so much.
Thank you very much, Lyndon, for a terrific presentation. I hope people will go over to the journal website and take a look at the full paper. As a reminder to our audience, if you have questions for Lyndon or for any of our speakers today, please feel free to submit them in the side panel where you see a questions box. I will read those later during the Q&A session. Next, we move over to our second presenter, Dr. Yanyan Liu, who will present a very specific application of these methods. Dr. Liu is at IFPRI and is an adjunct faculty member at Cornell. Over to you, Yanyan.
Thank you, Chris and Lyndon, for your excellent presentation. So the paper I'm presenting is a joint work with Bingtang and David Madsen, who is also in this seminar. In this paper, we use vegetation index NDVI for poverty prediction. As Lyndon just presented, recent advances in remote sensing and machine learning technologies has opened up a new path for poverty prediction. Jin et al. And Ye et al. Are the two papers particularly relevant to our study. Jin et al. Is a seminal paper that uses static Google images and nightlight data to predict consumption, expenditure, and asset index at the community level. Ye et al. Uses dynamic Google images to predict asset index both over space and over time, also at the community level. Forgot to mention, Jin et al. Only didn't do over time prediction or sequential forecast prediction. There are two key limitations of using Google Images data for poverty prediction. First of all, Google Images cannot capture crop and rangeland conditions. This results in poor predictive performance among the very poor communities that rely heavily on agriculture as the main income source. As we know, in a lot of cases, we are actually care more about the poor communities than the richer ones. Second of all, Google Images change slowly over time. This results in poor performance for sequential prediction. For example, in Ye et al., when they try to predict a future period eyesight index, R squares at the community level, the R squares is only 0.15. Our study leveraged the NDVI at 250 meter resolution to estimate consumption expenditure and eyesight index at the community level, both over space and over time. NDVI provides a signal for crop health and rangeland conditions. Different from Google Images, NDVI is fast changing and correlated with well-being among the very poor. Methodologically, we follow Jin et al. To rely on CNNs and transfer learning using the nightlight data as intermediate labels. We have two key findings in the overspace prediction. The overall predictive power of our NDVI-based model is comparable to Google image-based model. However, our NDVI-based model outperformed Google image-based model in predictive performance among the poorer clusters. When we do sequential prediction, we predict the consumption expenditure for an out-of-sample period in Uganda and find that NDVI can effectively detect consumption variation over time among the poor communities. We made 3 contributions. First, we demonstrate that with CNN's publicly available moderate resolution NDVI images alone can predict poverty measurements as accurately as state-of-the-art methods using Google's high-resolution images with more than 4,000 features. Second, our model improves predictive accuracy among the poorest rural communities. To our knowledge, our study is the first attempt to predict future period consumption expenditure. Sequential prediction of consumption is especially meaningful for early warning because consumption captures current poverty, as Linden's paper has explained. In the remainder of the presentation, I'm talking about the data and then the method, the result, and concludes. So data first, our response variables are 2 poverty measures. The first one is consumption expenditure per capita at the community level from living standards measurement studies. It's a current poverty measure, and we use the 4 countries, Malawi, Nigeria, Tanzania, Uganda. The second measure is eyesight index with a chronic poverty measure. It's also at cluster level from demographic and health surveys. We have 5 African countries. We have 2 predictors used in this NDVI-based model. One is annual NDVI images. The other is nightlight data, which is used as intermediate labels for transfer learning. We also use Google daytime images only for comparison with our NDVI-based model. So our NDVI-based model actually only uses those first 2 data sets, not the third one. This picture shows NDVI in 2010, annual NDVI, and this area is the areas with high NDVI values. And this figure shows night lights in 2010 for the whole world. Night lights is considered a proxy for economic activities and development. So we have more development area, United States, which has high light intensity, and the dark area in less development economies shows in this area, for example. This figure shows an example of daytime satellite images from Google. This is location in Uganda. Then I'll briefly talk about the method. We use CNNs and transfer learning following a 2-step procedure to bypass a lack of labeled responses. In the first step, we fine-tune a VGG16 network in NDVI images to predict night light intensities in order to extract the NDVI features. In the second step, we fit random forest models using these NDVI features to predict consumption and eyesight at the cluster level. The combination of NDVI images and night lights allows vegetation features indicative of economic activities to be learned and generalized to the poverty prediction task. Next, I'll present the results. I'll talk about the overspace prediction first. In this analysis, we use cross-sectional data for individual countries. The results for response variable as the consumption expenditure presented in this table, we showed the cross-validated R-squares of NDVI versus Google image-based model. So we can see that NDVI has a comparable performance in prediction power between as images in two countries, Tanzania and Uganda. NDVI did slightly better, and the other two Google images did slightly better. Here we look at eyesight, the same analysis. This table again shows R-squares for the NDVI and Google images. Again, NDVI outperforms Google images in three countries, which are Nigeria, Tanzania, and Uganda. And in the other countries, Malawi and Rwanda, Google images did slightly better. Now we come to our first main results. In this analysis, we look at predictive performance by poverty level. We run the regression for separate samples based on their poverty status. In this figure, the x-axis shows the percentage of poor-risk communities included in this sample. For example, the 60 means we have the communities below the 60th percentile consumption are included in this sample. The y-axis shows R-squares. We can see that, oh, sorry, I forgot to mention the green curve is NDVI prediction value, and also the orange lines is based on the Google image model. We can see overall Google image model and the NDVI has similar performance. However, among those poorer communities, NDVI did better than Google images consistently. Now we look at eyesight index as the response variable. Here we did the same analysis, and we can see that NDVI-based model performed consistently better than Google image-based model among all of those communities, and especially NDVI's advantage is more pronounced among the poorer communities here. Our next result is on prediction over time. Here we use 209 communities in Uganda surveyed in two rounds, 2011 and 2013. So this data forms the panel at the household level and community level. We trained the random forest model on the 2011 NDVI feature maps and test the model on the updated NDVI features in 2013. The 2011 and 2012 is a severe drought year. This drought has affected a large area in Uganda. This figure shows NDVI measures for Uganda from 2007 to 2014. The gray area highlights the two drought years. And we can see the drought effect has been picked up by NDVI. We have sharp drops in those 2 years. So this figure shows consumption expenditure results from the sequential prediction. Here we focus on look at the upper panel first. And we rank the communities based on their poverty status in 2011. So 0 is the shows the poorest community, and 208 is the richest community based on 2011 consumption expenditure. The y-axis shows log consumption, and the orange line is the 2011 consumption level shows. The green columns shows the consumption level in 2013 second round. We see that there's a lot of variation in consumption over time. This is variation is more pronounced among the poor communities. 2011 had significantly lower consumption levels because of the drought. And the blue curve plots the predicted consumption level using our NDVI-based model. We can see that it captures the variation of consumption over time. So here we look at the performance of our NDVI model. Again, we look at the poor risk percentage of surveyed community used for different levels, and also the y-axis is RMSE, which is measures the prediction error. So the smaller the better. Our blue curve shows the predicted value of consumption, predicted error of our NDVI model, and the orange line is shows the naive model. So basically, the orange line is 2011 consumption level. So basically, using 2011 consumption as a predicted consumption level for 2013. We see, interestingly, this naive model performs similarly as our NDVI-based model for the whole sample overall. But if we look at the poor communities, our NDVI-based model shows much lower errors than the naive model. We have two main findings. First of all, our prediction over space shows that overall predictive power of our NDVI model is comparable to Google Images. However, our NDVI model outperformed Google Images in predictive power among the poorer clusters. The sequential prediction shows that NDVI can effectively detect consumption variation over time among the poor communities. There are three policy takeaways. First of all, it's important to include predictors that can capture crop and rangeland conditions if we intend to capture poverty dynamics among the rural poor communities. This highlights the importance of careful selection of predictors to serve the study purpose. Secondly, our study shows the potential to reduce the computational dimension using alternative data sets without sacrificing predictive power. This significantly lowers the technical bars for this kind of analysis. Also, it shows that advanced machine learning methods such as CNN combined with a suitable data set can push forward the frontier of the research on poverty mapping, early warning, and program impact evaluation. This highlights the importance of effective collaboration between economists, computer scientists, and remote sensing scientists. That's the end. Thank you.
Thank you very much, Yan, for presenting such exciting results. It's really cool to see how you can get much better performance among the poorest populations using some more appropriate data series. So thank you for sharing that with us. As a reminder to our audience, if you have questions, please feel free to submit them in the side panel at any time where you find the questions box, and we'll read them and the panelists will respond to them during the Q&A session. So next, our third presenter is Chris Brown. Chris is a PhD candidate in applied mathematics at Cornell University. He'll present another specific application of these big data methods to a range of countries for both nowcasting and contemporaneous poverty and malnutrition mapping. Over to you, Chris.
Hey everybody, my name is Chris, and I'm going to be just quickly going over a recent project that we worked on. So this project has been sort of tentatively, or is in the final stages of being accepted to PLOS One. And given the time constraints, I'm trying to keep this presentation pretty light. But if you have questions, feel free to ask them. And if you want more details, you can kind of go and read the paper on PLOS One in the near future. Okay, next slide. Okay, so the very high level idea of this project is that we want to use machine learning to predict and estimate poverty and malnutrition prevalence. And this can be useful to sort of both government and non-government agencies for a few reasons. It can be used for early warning, so detection of maybe famine status. And then it can also be used to sort of evaluate where maybe food-based or financially based interventions should be placed in a given country, and then to also assess how well those interventions are doing at reducing poverty or malnutrition. So historically, the way that poverty and malnutrition prevalence is assessed by agencies is via surveys, right? So they kind of just manually send people to villages and ask them how they're doing. You can imagine that is sort of expensive and not particularly fast, because you have to have people go to villages and walk around and ask people stuff. And so a sort of alternative that's become feasible in recent years is to potentially just use remote sense data. So you can imagine you maybe just have a satellite that's getting information about some location. And ideally, you can combine that with some machine learning or statistical method to sort of infer the affluence of a particular region. Okay, next slide. Okay, so just to give you a quick overview of the data that we're using for this, we used open source data sort of motivated by the desire to make this accessible to people. We have 5 different sort of outcomes that measure poverty prevalence and malnutrition prevalence. So asset poverty, child wasting, child stunting, underweight female BMI, and another one. And so then so yeah, I should just mention that these come from DHS surveys, right? And so then for our inputs, we use a few different data sources. We use meteorological and agricultural data. So SIF, CHIRPS, LST, these are all data products that are available that measure conditions related to either meteorology or agriculture, conflict data, and then also sort of just like basic location data. So like where is a particular location, right? It's like what is its latitude and longitude. And then finally, we use the IFPRI derived market food price data. All right, next slide. Okay, so as kind of mentioned earlier by Lyndon and Yan, so like state of the art and related works in this field tend to use either deep learning and or deep transfer learning. And so one sort of goal of this project was to test whether or not it needs to be that way. So can we actually just use maybe easier to implement methods or just alternative methods that might be more interpretable to do this prediction? And then it's also very possible that the outcomes that we talked about on the last slide might be correlated with one another. So it's not inconceivable that asset poverty could be correlated with things like child wasting, right? And so we also wanted to test whether or not a joint model could maybe improve prediction. And so in this paper, we use in particular a joint or multivariate random forest. And a sort of nice boon from using that method is it also lets us sort of identify what features are sort of key to predictive accuracy. All right, next slide. So the DHS surveys that we considered come from 11 different countries, partly in Africa, but also in Central America and Central Asia, I guess, West Asia, I don't know. And they come across about a decade of time. One sort of annoying thing is that the food price data that we have is sort of country specific, so they track different commodities in different countries. Because of that, we decided to do training and testing on a country-specific basis. So when we're making predictions for, say, Nepal, we only use data from Nepal to do that prediction. We don't use data from, say, Guatemala, right? And we considered 2 predictive tasks in the paper. The first is contemporaneous prediction. So the idea of that is to, let's say you have used surveys to generate estimates of poverty and malnutrition prevalence in certain locations. You might want to sort of extrapolate your estimates of poverty and malnutrition prevalence to other regions in your country that you did not survey, right? So you're kind of filling in the gaps spatially, but with time fixed. And then the second thing that we considered is called nowcasting. So this is generating short-term forecasts of prevalence using historical survey data and then like present remote sense data. So you'll have surveys from the past along with like the current inputs to your model, and you'll be trying to generate short-term estimates. Okay, next slide. So I put this picture here just to give you kind of a visual idea of A, what predictions for a model can look like, and then B, the difference between contemporaneous and nowcasting. So I want you to imagine for a second that as like an administrator, you have surveyed all of the locations that are purple dots, right? So you sent people to the villages in those purple dots and you got estimates of poverty and malnutrition. So then for contemporaneous prediction, you might be interested in filling in the northern part of the country, right? Based on your surveys in the bottom of it. The reason why there's like gaps in our prediction is because there are gaps in our underlying features. And then for sequential prediction, or for nowcasting, sorry, I kind of variably refer to this as sequential nowcasting. So for nowcasting, you can imagine, so you've surveyed these purple dots, and now you want to either generate short-term forecasts for the purple dots, so locations you've already surveyed, or like areas that you haven't, so areas in the north. You can do either one with the nowcasting. Okay, next slide. Okay, so maybe this slide's overkill, but we decided to measure accuracy via out-of-sample R-squared, and then we use a slightly different metric than what is traditional. We use root mean squared error, but we normalize it by the observed prevalence range. So what this kind of gives you an indication of is like, if you look at your average residual, sort of what % of the range of the indicator does that cover? So if that number is small, it means that relative to the dispersion of the prevalence range itself, you're like pretty accurate. If it's large or not. And then this will be somewhat relevant. So when we were assessing the accuracy of our model, we considered 3 different sort of frameworks. In the first one, we pooled all of our predictions across every single survey into one big bin and computed these metrics. We also did this at a country-specific level, so for all surveys within each country. And then finally, we also report just like our performance on each individual survey. And there are differences in sort of our results at these 3 different levels of aggregation. All right, next slide. So just, I'm not going to really like go into the full predictive results just because we don't really have time. So one of the big takeaways is that unsurprisingly, contemporaneous prediction is easier than nowcasting. With nowcasting, you're kind of predicting shortly into the future. It's harder to do than predicting like, contemporaneously, right? Consistent with other work, asset poverty is a lot easier to predict than malnutrition prevalence. So this indicates to me that it just means that like we don't have good data for uncovering the dynamics of malnutrition prevalence. So that's maybe something people could think about is like what kind of data could we collect that would make this easier? And sort of the key takeaway I think that we found in this paper is that both joint and independent random forests actually do about as well as sort of the deep and transfer learning models for prevalence prediction, but only when those results are assessed in aggregate or at country-specific levels. And what we did find is that these methods do worse relative to deep learning and transfer learning at sort of what we term like early survey levels. So surveys that happen like early in time, let's say like 2003, 2004. The reason for this is due to small sample size. So if we have small sample data, if we have small data, the random forests do worse than the transfer learning methods because they are sort of less reliant on sample size. All right, next slide. And so I put this in just to kind of like make that last point more clear. So these are nowcasting results at the individual survey level. So each dot is like, what was our out of sample R-squared for that particular survey? And there are 5 dots because there are 5 outcomes. The x-axis is survey size, the y-axis is R-squared. I want to emphasize these are actually our worst results in the paper, but I just wanted to include them because they're most visually demonstrative. And so you can see like, as a function of the survey size, when you have a very small survey size, sometimes this model does very, very poorly, right? You get like very low R-squared. But once the survey size gets above like 600, 700, you stop seeing that occur. And in general, you start to like get consistently acceptable or higher R-squared values out of sample. And also, you can also note that asset poverty, the red dot, generally the highest one, right, on each line, right? Okay, next slide. Okay, so sorry, I need to move something. Okay, sorry about that. So yeah, the sort of exact performance of our model varied quite a bit based on prediction regime, so contemporaneous or nowcasting, how we pooled the data, and the exact target outcome. But one thing that was kind of interesting that we found is pretty much regardless of those things, our normalized root mean squared error was pretty low. So it's generally on the order of 10 to 20% of the observed indicator range. And so what that implies is like for a first pass, this method seems to actually pretty consistently generate what we call tolerably accurate estimates of poverty and malnutrition prevalence, in the sense that if you were like an administrator or something, using these methods would like give you a qualitatively reasonably accurate understanding of the poverty and malnutrition prevalence in a region, pretty much regardless of, you know, again, like contemporaneous prediction versus nowcasting and like how you pooled your data. We also found that, so joint prediction did kind of help a little bit. So mainly in the nowcasting framework, it sort of produced slightly better estimates of some of our prevalence rates. So it's like a potential thing that I think people could investigate further. It wasn't huge, it wasn't a huge difference, but it did seem to give some predictive power, right? Okay, next slide. And so then the last thing I wanted to talk about, we mentioned earlier that using the random forest lets us kind of assess variable importance. So the y-axis you can just interpret as like how important is this variable. The y-axis could be as 1, which would mean like this was the only feature that mattered for this model. What you can see immediately from this, and I'll talk about this a little bit more on the next slide, but what you can see immediately from this is that as far as our model is concerned, the most important thing for doing estimation is actually where in space a given location is, and basically like, is it a rural region, right? These sort of like higher, I don't know, variability variables like vegetation and weather data were also relatively important, but the bulk of the work here is being done by location or remoteness data. That causes some problems, I think, in terms of like people being satisfied with these results, maybe. Like, I'll talk about this a little bit more on the next slide. So yeah, let's go to the next slide. So yeah, like basic location data is the most useful. I think the reason why people might find this a little bit dissatisfying is it's a sort of non-causal description of the underlying dynamics of poverty and malnutrition prevalence. That being said, it's just like really effective. So for short to medium term time horizons, this seems like a really useful way to predict this. And I should emphasize that like this is basically the model just saying like I know in space where poverty is, and so I assume kind of that there's spatial correlation in poverty rates and malnutrition rates. You can imagine that that will work a bit less well in heterogeneous areas. So if there are actually areas where poor and relatively wealthy communities are sort of intermixed, this model might do worse. And you can also imagine it could sort of fail to extrapolate properly in certain cases. But again, like other data was useful, specifically the meteorological and agricultural data. And I think the food price data could have been more useful. So because, like I said earlier, the actual quantities that were tracked by IFPRI varied across countries, I don't know, like it wasn't always standard even within a particular country. Also, I don't think that there was very good overlap between the market locations and the survey locations for DHS. So like, I think that the food price data could be a lot more useful, but it might, like its collection might need to be somehow altered to be made more useful. So better coverage of markets and like consistent collection, basically. Okay, next slide. So that's basically it. You know, just to sort of bring it home, like it seems like the random forest models with our data set, the open source data, can generate relatively accurate estimates, so tolerably accurate estimates. And again, like these estimates are basically on par with state of the art for particular frameworks. So when we have a lot of data, but they don't do as well in small data sets. I think one conclusion to be drawn from this is that like, even though we would like to sort of remove surveys entirely and just use remote sensing, we're kind of not there yet. These things need to keep on being done for a little while. And so yeah, joint estimation could be helpful, and a contemporaneous prediction of asset poverty is sort of the easiest task. Okay, thanks.
Thanks very much, Chris, for a really interesting presentation. And again, as a reminder to our audience, if you have questions, please feel free to submit them in the side panel at any time where it says questions box, and I'll come to those during the Q&A session. But first, we're going to get to hear from our discussant, Dr. Rob Voss. Rob is the Director of the Markets, Trade, and Institutions Division at IFPRI. under which the food security portal sits. Over to you, Rob.
Thanks, Chris, and thanks to all the presenters. This is really exciting new research. I would say probably path-breaking new research that's a clear response to our needs for getting more timely data on poverty, food security, malnutrition, particularly understanding the risk and vulnerability factors causing these outcomes. And as several of the speakers pointed out, so now we're pretty much reliant on pretty costly survey data, which doesn't come with sufficient timeliness and maybe also pretty much behind the realities that we need to address. So, for instance, the recent publications of the impacts of COVID-19, global poverty, and food security, for instance, they're all just basically based on projections or very case-based observed data. We have the new studies from the FAO and other organizations on the state of food security and malnutrition in the world, estimating that food insecurity is on the rise and hunger is on the rise, but basically based on pretty much indirect methods of estimating what including the impact of COVID-19 has been. So we really need better early warning systems to be able to respond timely and in a well-targeted manner. So in that sense, all the papers present quite a bit of progress towards something that could lead to, call it real-time monitoring of poverty and malnutrition. Now, before getting to the various papers specifically, I would like to commend Lyndon, particularly Lyndon McBride, on asking the question, okay, what are the models actually supposed to measure and what are they trying to do? Because I think that's essential to see whether this new work can lead to applications that are also policy relevant. That's in the end what we would like to see happen. So I think it's very important to raise the question of what precise poverty concepts we use, what food security concept, and several have been mentioned, and across the papers, different concepts have been used. Now, maybe it's a comment on Lyndon's paper and presentation is how do these concepts link to what policymakers are looking at? So policymakers, where it comes to food insecurity, they either look at acute food insecurity, that's a concept particularly in use of for the food crisis, and for instance, the global report on food crisis and a lot of the early warnings mechanisms are focused on that concept, which is different from the chronic concept, which is more standard in use for the prevalence of undernourishment, for instance, or the food insecurity experience skills used by international organizations. So I would recommend to translate some of the terminology that's being used in the paper by Lyndon, but also in the other papers, to those concepts. Likewise, for structural versus transitory poverty is another thing, another set of concepts used in the literature on poverty. The concept used in Lyndon's paper is a bit closer to actually the methods that were used rather than the policy concept. So that translation, I think, was missing either in the presentation and in the paper. Second thing is how you would look at other policies issues like mapping and targeting. I think that's very clearly brought out in Lyndon's presentation. But I would say in practice, there's not much, I think the dichotomy is not so much between mapping and targeting, right? So it's a lot of targeting of policies, poverty policies, social policies, is done through geographic targeting in the past, and that's why also poverty maps have been designed for that reason way back in the 80s. So maybe that dichotomy is, as put in the presentation, is useful from the perspective of the methodology, but could be confusing from a policy perspective. So particularly so that the targeting can be done at geographic level, could be done through means testing at the individual levels, and so it's the mapping of where people are and what their economic status is should be done probably both, and in order to meet policy needs. So another suggestion for refinement. I think what is very interesting is the move forward to using artificial intelligence and machine learning. So the question is well, what are we trying to predict, and what is in the original data is properly observed data, and what is actually also partially statistically or model based. So for instance, with the poverty maps in the observed data, just to get to very detailed granular data of locating the poor, that in the past was done by linking population census data with household survey data, and then get through partial modeling exercises onto estimating the degree of poverty at pretty granular local levels. But of course, in between there's some sort of assumptions there. So it's very important to make clear whether the data that we're using, to what extent it's truly observed data, and to what extent it's constructed data indirectly from the other types of data sets. And I mentioned that it's very important to make sure that the methods and the measures are very clearly defined and transparent for policymakers, but also for the beneficiaries. Let me come back to that towards the end. So I think it's, in summary, on that point, it's very important to emphasize the issues that were raised in Lyndon's paper, but I think the missing element there is to translate her conceptual approach to from the methods being used onto what policymakers use in terms of their concepts. Then the papers presented by Jan and by Chris, I think very excellent papers, very interesting work in showing how we can get to fairly good estimators or predictors of various poverty and malnutrition concepts. I just have a couple of questions there, which are again of importance both to policymakers, but also in terms of the approach used. The one is it has to do with the implicit assumptions about what are the predictors. So if we look at the vegetation index study and the one applied by Chris, they seem to be more applicable by assumption to subgroups of the poor, right? So Jan mentioned the very poor, but it's also particularly apt for agricultural and rural contexts. So the question is then, what does it mean for the method at large, particularly when we use vegetation as one predictor, vegetation coverage as one predictor of these outcomes? Is that relevant more across the board, or just for when we're interested in a particular subgroup of the poor or the malnourished? Then, and more specifically, so if we look at, and that may be a related question, is what's the implicit theory or model behind the predictive model that you lay out? So if we just look at the vegetation link, what are we assuming is that because lesser less dense vegetation could be a predictor of poorer harvest or lesser agricultural productivity, and hence through that on poverty and on malnutrition. So the question is, okay, what's the implicit thinking behind that, and whether if we just look at this association with vegetation, that we can explain sufficiently well to inform policymakers. Of course, likewise, if we would do the nightlight density, one would suspect, okay, that more density is associated with greater development, more infrastructure, but potentially also with less vegetation. So then the question is, well, if we both find that more dense vegetation and more dense nightlights would both be a predictor of less poverty, then how would that work in practice if maybe there's less dense vegetation is associated with more urbanization at the same time? And I could raise a similar question on Chris's paper, which also was focused on agriculture, food prices, and conflict, which seems to be looking at associations which naturally are there. It's also been found in the range of more descriptive studies in the Global Report on Food Crisis and so on. But still, it's important for policymakers to identify why one select those determinants rather than potential other causal risk factors. And that brings me to a broader point for the overall approach. So I think this is enormous progress that we're making in trying to predict poverty levels. But the question is whether we should subsequently not much more focus on, okay, what are the potential risk factors that drive to those outcomes? Because what policymakers can enact on are the risk factors, right? And try to, particularly when it comes to more structural approaches to addressing these problems. So shouldn't we also try and predict, okay, how do these risk factors change over time, and then on to looking at the impacts on poverty and food security. Lastly, that's more a technical question on the level of detail, particularly what in Jan-Jan's analysis and Chris's analysis, who focus on the sample size of existing information. So first question is whether the cluster level is a refined enough level to make these predictions, and also whether the information that we have on the dependent variable, meaning poverty and food insecurity, is sufficiently reliable at that level, given the way the survey data and the samples have been designed. It also applies to Chris' data, maybe Chris's observation on this notion of samples size, that I understand that if a smaller sample size gives you less observations, so hence for the analysis undertaken less variation. But a smaller sample size not always means less accuracy in the observations that we're interested in. So it might be also a suggestion to look beyond not just at the sample size, but rather at the sampling errors that are come out from the survey data that are being used to estimate the dependent variable. Let me close with a few remarks of what's the upshot of this. So what and how to move further. First, I think this is exciting work and can lead to more real-time and more timely data for policy responses. But at the same time, when we think of the predictive value of these models for poverty and food insecurity, then we also should take into account is that even if policymakers do not have accurate data, they may still be enacting on perceived policy problems. So we may also have interdependency issues with policy responses that are not being accounted for when we just look at the indicators or the explanatory variables that we have been looking at. So particularly it's important that we also look at those variables, what is the policy context and the response capacity, in order to see to what extent the other variables that we can and trying to measure more in real time are not also influenced by these policy responses. A second general comment is that I think there's a enormous future for this kind of work, also to inform policymakers. But at the same time, given the uncertainties we have, also with what we can predict now, is the need for better observed data to validate also these predictive models. So what we know from the past may not be a good predictor of the future. So we continuously have to validate these models also because conditions and conditioning factors may change over time. The third point is, of course, when we think of predictive models, as it goes with economic forecasting more in general, even what we know works pretty well in many cases are macroeconomic forecasting models in what we call normal times, but those models typically get it all wrong when there are unexpected shocks, so like COVID-19, but even many droughts can not be that predicted well in advance, such that we may still be falling behind the curve with our model if we cannot properly monitor the risk factors at hand. And then lastly, and coming back to my first points, it's very important that we have good concepts, but also transparent, particularly when they're going to be used for policy responses or targeted interventions, so that the identification or who are eligible for support measures, be it through food assistance, social policies, or other interventions, that it's very clear is why those groups are being targeted and others not. So let me leave it at that. So I think it's very important progress moving forward, but still quite a long way to go in order to get to good real-time monitoring and predictive models for food security and poverty. Over to you, Chris. Thanks.
Thanks, Rob, for a really excellent summary of key issues raised by these three presentations and the underlying papers, and especially for connecting these relatively technical issues back to policymakers' needs. If I could now ask all of the speakers to please turn your cameras back on, it's time to open up for questions and answers, both to Rob's discussion of your presentations and to audience questions. And to the audience, again, if you have questions, please feel free to submit them in the side panel at any time where you see questions box. So why don't I begin with just inviting each of you in turn for just 1 minute. Any key responses to the good points Rob raised on each of your papers? Why don't we go in the same order of presentation? So Linda?
Yeah, I also really appreciated Rob's point about mapping our sort of academic exercise onto policymakers' needs. That's a great comment. I do want to circle back to the targeting versus mapping distinction. I absolutely agree that mapping is fruitfully used for the targeting of policies and programs. However, part of the impetus for this paper is I get asked to review a lot of household or person level machine learning informed targeting models that use 45, 60 features to produce the model. Now, a targeting model, a household level targeting model, that uses a feature set of that magnitude would be extraordinarily costly for an agency to implement, because it would mean having a 60-question survey that they would need to ask each potential beneficiary household, which is for some agencies that may be in their best interest, which is why we try to highlight the agency's objective function. But for most agencies, that's going to be prohibitively costly. So, for proxy means test targeting type models, a lean model is in generally the agency's best interest, because it's far more cost effective to implement. Now, that said, there are important trade-offs between the predictive accuracy and the costliness. And that, again, is something that the agency needs to define in terms of their objective function. So I agree there's nuance there, but the distinction is important.
Thanks, Linda. Yanya?
Hi.
Responses to...
Okay, thank you for Rob's excellent comments. Let me respond for his first two questions on my presentation. The first one is about the context when NDVI should be used. Oh, I'm sorry, I don't know why I turned off my camera. And yes, I think you are right. So this advantage of NDVI is to predict the poverty measures among the subgroup of the poor communities. As we mentioned, we know it's in many cases those are policymakers, what kind of policymakers actually care about. And also, it's more relevant to agriculture and the rural context than in the urban context. Also, it's important to understand the implicit economic rationale behind the black box of machine learning. I think it's so Chris Brown's presentation, I think it's complementary to my presentation, because in my presentation, our work, we only use NDVI and night lights. And Chris Brown's, we use different data sets which capture different, risk factors on the outcome variable, predict the response variable. So I think the pathway to move forward is to carefully select what data sets to use based on economic rationale. And also regarding to the sampling errors, I think that's an excellent question. Actually, I think it's about measurement error. And usually consumption expenditure is noisier than eyesight index. That's probably one reason that in most of the analysis, we found that the predictive power is higher for eyesight index than consumption expenditure. That's related to your comments on measurement, what outcome variable to measure for this kind of study. So I think besides eyesight index, people have been using like a food security score, etc. And those are the indicators which are easy to measure and tend to have lower measurement errors. I think it's probably more suitable for this kind of analysis. Thank you.
Thanks very much, Yan. Chris Brown, do you have any responses to comments Rob offered on your presentation?
Actually, I wanted to just ask him, Rob, what was the point that you made on sampling error in small sample sizes?
Well, because sample size depends on the sample frame, right, and what you need to design. So the size of the sample depends on the population size, but so it not necessarily is the smallness of the sample gives you less accurate data, right? it may give you less observations for you to work with, right? But it not necessarily works. So what I was suggesting is you combine the sample size, right, with maybe a limitation to the kind of analysis you do, with the sampling errors of the survey, right? So and particularly variables like poverty, food insecurity, sort of they may not be the main objective variable of the survey, right? So they may have rather big sampling errors. So that was the point I was trying to make. So there may be, and it applies to all the studies, right? So not like you have a poverty number in a particular sub area of the survey, but there's probably a range around that confidence interval that's defined by the sampling errors.
Oh, sure. Yeah, that's a good point. Yeah. I guess that's my only comment right now. Yeah.
So maybe let me follow up on that point, because I think Rob's good point about sampling error in small samples, that you're trying to fit these models to a sample prevalence that is a noisier estimate of the true population prevalence if you have a small sample than if you have a large sample. So it's not surprising that you get worse fit. Parallel to that is a question not about sampling error, but about measurement error. There's a rapidly growing literature that emphasizes how rife household survey data are with measurement error, in particular with non-classical measurement error. And that raises all sorts of questions, because it means that assessment of predictive accuracy of these machine learning-based methods, where we're using the survey prevalence rates as the benchmark, we could be substantially understating their performance. It might be that the machine learning exercise is actually getting the population figure right, and the sample is wrong, the survey sample is wrong, because of measurement error, sampling error, both. What can be done to overcome the challenges again of benchmarking predictions against error-ridden survey observations, or at least overcoming the reticence to embrace machine learning-based methods because of understated goodness of fit? Any thoughts? Lyndon, I suspect you've been giving this issue some thought. Chris, go ahead.
I mean, yeah, maybe this is naive. I don't see how you can solve the measurement error issue unless you just survey more households, right? Because each of the actual prevalence estimates is actually a weighted sum across different households in a cluster, right? So I mean, I would think that you just need to include more households, and then that should reduce the measurement error.
I would say not
that should reduce sampling error, not measurement error, right?
Oh, okay, right. So the actual households might be reporting incorrectly. Is that what you're getting at?
Exactly.
Okay.
Yeah. That's and those errors are largest in relative size in the poorest households and the smallest farms, it appears in the literature.
Okay. Yeah.
But of course, maybe an interesting point within this literature is also how the surveys are designed, right? So if you have complex household surveys, the likelihood that all types of consumption are poorly measured, and we know when it comes to incomes, people, when asked about, tend to lie about their incomes, particularly at the higher end, things like that. So, but if you take what could be an important step forward, methods like the Food Insecurity Experience Scale, which FAO is now applying, which is basically an 8 binary questionnaire, right? There's 8 questions, just yes and no questions, and about their food security situation. And food consumption scores, also applied by others in FuseNet, go in that direction. So that's easily implemented as long as you just focus on that, right? Of course, there's a whole ton of other things have to come into it. But then if we do that in a refined way, we may get more accurate estimates of our dependent variable, and can worry more about, okay, what are the risk factors and the causal factors that we would like to bring into account when predicting these numbers, right? And but even then, that said, then we can probably predict what's observed, right? And so then the question is, okay, now how can that tell things about the future? And that's what's the point that was raised early on focusing also on how can we assess the risk factors, so we can then assess, okay, that likely will lead to more poverty or less or more food insecurity in this particular context.
We have a question from Gokul Paudel. My apologies, Gokul, if I've mispronounced your name. I'll summarize his long question. He suggests that these methods are very important, but how important is feature selection to predict poverty? And what are the key features that have been considered in this literature using machine learning and remotely sensed data? And relatedly, are latitude and longitude good features to predict poverty? Don't they just correlate with lots of other spatial data? Lyndon, I think this speaks to some issues you raised, and Chris and Yan Yan, perhaps you can chime in afterwards with your thoughts.
Thanks, Chris, and thanks for the question. So this is one of the tensions that we highlight in the paper I discussed. Feature selection can be entirely driven by the algorithm that one chooses, right? You can feed the entire data set, multiple data sets into the algorithm, and given the algorithm's objective function, you're going to get a highly predictive feature set at the end of the day. The question that we want tool developers to ask is, so when it comes to targeting, is this feature set one that can be turned into a survey where the data are easily observed, easily collected, in a rapid and cost-effective manner? If it comes to mapping, one of the questions you might ask about the feature set is, are these features determinants of structural poverty, long-term poverty, chronic poverty, malnutrition, or are they correlates of current or stochastic poverty? And this might be the difference between what someone's house is built out of, that would be a correlate of long-term and chronic deprivation, versus whether they ate meat last week. That would be a correlate of current or stochastic poverty, malnutrition. So to answer your question, yeah, the feature set can be completely selected by the algorithm. We would encourage model developers to think carefully about the underlying welfare dynamics behind the features. I don't know if I've satisfactorily answered the question. Did I get everything?
Yeah, that's terrific. Thanks. Yan Yan, any thoughts?
No, I don't have anything to add.
All right, Chris, do you have anything to add to Lyndon's response to Gokul's question?
I have one request. I mean, you don't have to do this. Can you paste the question into chat so that I can actually look at it? It's okay if you can't.
Sure, it was in the Google Doc online.
Actually, the question does ask about.
Here, I just put it in there.
Yeah. Okay. So go cool. To answer the last point, latitude and longitude. I mean, you basically kind of already brought. I don't think that they're very good features for prediction. They literally work well, right? But what you're mentioning is important, which is that they're really just getting at other spatially correlated variables that are hidden to the model, right? It's it's not like people, are poorer because they live at this particular latitude and longitude, right? It's that there's some hidden variables that, are actually discriminating those people from wealthier regions, right? So ideally, right, we would just have other features that make it so that latitude and longitude are not important, but we don't have those right now. For how important is feature selection? It is relatively important, right? Because so you're going to have all these features, you're going to be fitting a model on all of those features, and that model will have parameters sort of proportional to the number of features. So unless you have a ton of data, you're generally going to be running into an overfitting issue. So you need to do some kind of variable selection, I think, either before fitting the algorithm or concurrently with it. Again, that concern is mitigated if you have a ton of data, but we don't have a lot of survey data right now, right? Let's see. And then what are the key features that have been considered? I mean, yes, the big ones have been like these like sort of satellite-based images, like satellite-based features. So, nightlight is one of the big ones. Measurements of, people's electricity usage, basically. And then, the sort of vegetative indices, NDVI, SIF. I would say those are the big ones that people have mostly looked at. And then in the random forest paper, we looked at some other ones like conflict data, market data, et cetera. But a lot of papers have used a lot of different features. And like, I would say that picking sort of reasonable features and assessing like what features are actually informative is like a pretty important task for the field. Yeah.
Great. Well, thank you, Chris. So this transitions us to the last question, which segues to a presentation by Mehta Bulumullah from Cornell, who will walk us through the website and the annotated code. Stephanie Kagone, and my apologies, Stephanie, if I've mispronounced your surname. She asks, what kind of services, systems, and software are used for machine learning modeling efforts? So Mehta is going to walk us through now the project website from Cornell, where you can find the various papers and presentations and annotated code. And she will briefly talk through the annotated code that's available to help users adapt the methods you've heard in this talk to their own applications. So over to you, Mehta.
Mehta, you're muted.
Sorry about that. Okay, so hi. So here is the project website, and you're going to find like papers and presentations and the slides from today. So next slide. So you can just find briefly about the research team and a lot of the people that talked today. Next slide, please. So we talked about different papers today, like predicting poverty and malnutrition for targeting, mapping, monitoring, and early warning. So that's there, even though it's not on the slide. And also the paper that Chris Brown talked about, the multivariate random forest prediction of poverty and malnutrition prevalence, that's also on the website. Next slide, please. You will also be able to find the presentation for today and the recording from this webinar and the last webinar. Next slide. And here's some data sources. Doesn't really reference this webinar today, but you can find different information from last one. Next slide, please. Okay, so there's also the code and the user guide. So Chris Brown talked about the code from his paper, and once you press on the first image here, there's like a code place, so you can click on that and that will lead you to the translational user guide. And this gives you both the Python code from the paper and also an annotated guide. And I'll show you just a little sneak peek of what that looks like. So next slide, please. So this is just how to use it. So you're just going to download, there's a Word document and there's also a Python file. So the annotated document is a Word document and it has black text, which is just the annotations, and the gray font is the code. You can obviously just delete all the annotations, but that's a lot of work. So just take the Python files and you can compile that there. So the annotations pretty much goes over what is going on in the code. So it kind of gives you a easy way to understand what is happening and also how to recreate it. So what you should change and alter depending on your data set. Next slide, please. So here is the contemporaneous forecasting, and you have the annotated guide, which is on the left, and then the Python file that you can press, and you can just view it from the website itself. And as you can see, there's the black text I talked about and the gray text, which has the actual code, and it kind of gives you a description right before the code of what is going on and what you should change. Next slide. And finally, here's this sequential nowcasting, same thing, annotated guide and the Python file. And you have a different, obviously it's a different code, and this will help you figure out what you need to change when or if you reproduce this and use different data sets and different information, and it will be very helpful when trying to understand the code and also reproduce it. Thank you.
Thanks very much, Amanda. Let me get the webcam up. So let me just encourage people to go to the website to be able to see the presentations and papers you heard about today. Let me remind you the event recording and slides will be available on the Food Security Portal's website as well as the Cornell Project website. And let me just close by thanking again our speakers and Discussant for their excellent presentations and terrific remarks, and to the audience for attending the event. Have a great day, everyone. Take good care. Bye-bye.
Thank you. Bye.